Okay, if you're given the graph of an exponential function, y equals ab to the x. Okay. Can you identify the value of a and or the value of b from the graph? Assuming their axes are scaled, okay? You got some kind of scale on your axes. Matter of fact, go ahead and put a scale on this axis with 8 here. And let's put 4 here. Now, anybody want to tell me approximately what A is? Okay, so in estimate, their first estimate was 3, but I put 4 and 2 on there. The first estimate was 2. I put 4 here and 2 here. Then the estimate got changed to 3. So I can sketch horizontal line through the y-intercept. This, of course, is y equals a b to the 0, because this is the x equals 0 point. That's just equal to a. So there we have a. If you've got a scale on a graph of a b to the x, and that almost looks like b to the negative x, something in the board there. It's a b to the x. Then you can immediately read off a. Now, how are you going to find b? Okay, we got someone who wants to volunteer. So now, in general, I mean, the answer I got is you just take some point on the graph. You got 8 here, you got 1.736 here, and you plug those numbers in, and you plug the x value in here and the a value here, and you figure out what b is. Okay, we're going to do that in a minute. But in more general, what I say is, if it's convenient, okay, here's 4. So here's 2, here's 1. Here's x equals 1. Oh, what is y equal to on this line? Well, if x is 1, what is a b to the x? It's a times b, isn't it? So this is y equals a times b. And now, well, which is bigger, a times b or a? Here's a times b. It looks like a times b is not quite twice as big as a. Maybe it's 1.6 times as big. Okay, so we estimate AB is about 1.6 times as big as A. You might think 1.5, 1.7, 1.4. So the only way A times B is going to be 1.6 times as big as A is if B is 1.6, right? And that's common sense. You don't even need an equation to do that, but we can say this, okay? If this is 1.6 times as big as this, then when you divide them, you get 1.6, and B is 1.6. Here's an algebraic solution. One way or another, though, you got to estimate. Okay, so now thinking that A is approximately 3, which is the estimate that we got. We got our formula, okay, got Y equals Y equals 3 times 1.6 to the X. Now I did a lot more with this in MDE, okay? And we started with a graph that had an asymptote that wasn't the x-axis. So all this is pretty simple once you have the asymptote to the x-axis, right? Well, if the function is y equals ab to the x plus k, you can subtract k and just get ab to the x, right? That means you just lower the graph k units, and now the asymptote is the x-axis. So if this white graph is ab to the x plus k, these arrows here lower it k units because k is what? K is wherever the asymptote is. Okay, the asymptote's this white dotted line here. So that's horizontal asymptote. That's y equals k. If you got a scale, you can estimate k. Lower the graph by that distance, and then you just do what we just did. Okay. Now all that's all jumbled up on this, but there it is. And the other thing is, you might get lucky and have a curve like this one curve. Well, you estimate your horizontal asymptote. Then you lower it by k units, and there you are. You got this graph. And you just do all the same stuff, okay? And in this case, you're going to find that b is less than 1, because what it's going to come out is, well, graph is decreasing. You kind of know that that's less than 1. But if you go through the process, they're just a little more, okay? You got this graph. You lower k units, you get the green graph, okay? You really want a graph that goes above the x-axis. So you flip this green graph around to get the purple graph. Now the purple graph, the green graph gave you the value of A. Okay. The intercept is your value of A. This is absolute value of A times B to the X. And absolute value of A is up here, just as far above the axis as A is below. And magnitude of A times B is here. And from this and this, you estimate the value of B. And it's fairly easy to do. Okay, now you're going to need to look at the video because I didn't really explain that. I just kind of pointed it out. So if you really want to get that kind of a graph, you can look back at what we did there. Okay, because we do need to go on with some other stuff. Okay, well, hopefully I recorded what I thought I recorded. Okay, just reviewing now. Toolkit exponential function has this table, this graph that you know how to construct. Okay. We want to do the inverse of the toolkit exponential function. I assume you understand everything you see here. But how do we do the inverse of a function if we have a table? Okay, now very early in the semester, we created graphs of inverse functions. We just switched the columns. So that our 1/4, 1/2, 1, 2, 4 go here, -2, -1, 0, 1, 2 go here, and we graph these points. We did this with the squared function, William. If we do this, you can figure out how this should be constructed, but it's pretty simple. We just take this rectangle and flip it over on its side and we get everything we need. I'll go ahead and do that, but I don't know how good it's gonna look. Because first place, my 4 here, a little bigger than the 4 here, so it's not gonna be absolutely symmetrical still. Notice that our x values now go from a little more than 0 to 4, right? So we need line x equals 4. We got the line y equals 2. We got the line y equals -2. So right here is a 4 by 4 square that we can subdivide. So we subdivide it here and here and here and here. And let's see, 2, 1, yeah. And then okay, we got our y equals 1, y equals -1 lines. Now we have a scale that allows us to locate these points. -2, 1/4, okay? That 1/4 -2. X is 1/4 here, y is -2 here. So there's 1/2 -1. There's 1/2, and there's -1. 1, 0 is here. 2, 1 is here. And 4, 2 is out here. And there's our curve. This curve is kind of a reflection of this curve through a line that makes a 45-degree angle. Now my scales aren't quite equal. My y scale is a little compressed compared to my x scale. So it's not a perfect picture, but you're going to see a nice picture when you look at the open math. Now, all this just comes out very simply by this is what follows if you switch the columns of this. Okay, now let's graph. Inverse of y equals 2 to the x is y equals log base 2 of x. And the logarithmic functions. First place, you can calculate the values of logarithmic functions on your calculator. You don't need to calculate the values for x equals 1/4, 1/2, 1, 2, 4. Okay, for any power of 2, and the value is actually just the exponent that you need for 2 to the x to equal one of these things. Okay. And yeah. Okay. Log base 2 of x. Okay, we are going to have to use a calculator in these. It's like you have to use a calculator to do square roots of anything but a perfect square. Now, there's a rule for log base 2 of x. To do this in your calculator might well have a log base function. Calculator you get to use in the test doesn't. So for that, we're going to need to know that this is log of x over log of 2, or natural log ln of x over ln of 2. Now, at this point, you don't know what log log means. You don't know what ln log means. Okay, log log is pretty much impractical to graph. It gets way steep, way quick. Okay. Natural log is fairly easy to graph. Okay, it's not much different than the 2 to the x. It's between the graph of 2 to the x and the graph of 3 to the x. you could graph either of those and then draw a graph that's a little closer to 3 to the x. And you would get the function that this is the inverse of. Okay, well, you don't need to know that. I'm just telling you that we'll be able to make sense of these. But first, we're going to do with log base 2. Okay. And then the open math will give you a little bit more. All right. Let's say now, again, this is the inverse function. It's a log base 2 function, has a graph looks something like this. It may be calculated as log of x over log of 2 on any scientific calculator, okay? Or if you like, ln of x over ln of 2, the log and the ln are usually on the same key. And one's like a shift or whatever. So it's really easy. You can do that. What I want to do now, though, is say what I just said over here. Except instead of using y and x, I'm going to use a and c. Say c equals 2 to the a, and just like y equals 2 to the x, is equivalent by a equals log base 2 of c. Now that's just saying the same thing I said over here. Except letting y and x be c and a. Now, as follows. Let's apply this. Well, it's all 2 to the x equals 5. Mechanics of this is very simple. Okay, is 2 to the x equals 5 of this form or of this form? I'm going to think this. I'm going to think this. I'm going to think this one. I'm going to think this one. Yeah, this doesn't have any log in it. It better be this. Okay. Okay. This is the form. C equals 2 to the a. For what value of c and what value of a? Okay, to identify a, for example, where does a occur in this form? It's the exponent on 2, right? Now, the equation that we're working at, what's the exponent on 2? It's x. So a equals x. And what's c equal? Well, c equals whatever's on the other side of the equal sign, which is 5. The equivalent form is a equals log c, log 2 of c, which is the same as what? Well, a is x. And c is 5. So replace A with X, replace C with 5. That's all there is to it. Then you go to your calculator. Okay, if you have a calculator handy, you can go ahead and do it. You get the log of 5 divided by the log of 2 by the rule I gave you here. If you like the natural log, that's fine too. It's going to give you the same thing, whichever log you choose. Don't use the log log here and the natural log here. Okay, whatever you use here, you do it. Okay, log 5 over log of 2. Okay, well, let's just estimate this. Here's our graph of the exponential function. And we want to estimate the solution to the equation 2 to the x equals 5. This function is y equals 2 to the x. Here's y equals 4. So I guess y equals 5 would be about here. This graph would go on up here and would intersect this graph at x about maybe 2.3. Is that what I just did? Yeah, I extended the graph of the exponential function. I drew a line for y equals 5. I drew the vertical line there and estimated that's x equals 2.3. Here's x equals 2. Here's x equals 4. That'd be x equals 3. 2.2, 2.3. Okay. And I say, well, according to the graph, that ought to be something close to 2.3. Okay, well, nobody's got a calculator handy, I guess, but it's okay. You can check me on it, though. It's always fun to check my estimates. I think it's probably closer to 2.2, but it's okay. It's easy to do this in a calculator. Okay. Do another equation. Two to a 3x minus 4 equals 5. We identify A and C. Now, it's still of this form because we have 2 raised to some power. Okay, so the form C equals 2 to the A, where A is 3x minus 4, the exponent, C is 5. The equivalent form is A equals log base 2 of C of 5. Let me write it. Three x minus 4 equals log base 2 of 5. Yeah, we estimated that that's 2.3. I could put 2.3 in here, but I don't want to. I want to solve this equation before I use my calculator in this. Okay, so we've got 3x minus 4 equals log base 2 of 5. add 4 to both sides, we get 3x equals log base 2 of 5 plus 4. So we get x equals log base 2 of 5 plus 4 divided by 3. And now we go to our calculator and do log of 5 over log 2, add 4 to that, divide the result by 3. Very straightforward. Okay. Well, that's great. Okay, one more equation. 7 to the 2x plus 3 equals 396. It's of this form, so we can translate it to this form, and we get instead of log base 2, it's log base 7 because the base here is 7. And we solve this for x, add, subtract 3 from both sides, divide by 2. And then explicitly, I'll say this is equal to log base 7 of 396 over log of 7 minus 3 all divided by 2 equals so forth. Okay. Now log base 7 of 396 is a little over 3. So that's going to be a little over 3 minus 3 divided by 2 is going to be maybe 0.05, 0.07, something like that. But whatever. So what I can do is I can generalize this rule. Where instead of 2, I've got b. So there are 3 things to identify in general. You got A, B, and C. B is your base, and then A and C go where they go. So you translate from one to the other. Now you translate from this form to this form as well. You'll see examples of that. It's equally easy. So it's really pretty easy. You just learn to identify your A, B, and C. And for the crank. Okay? And out comes your answer. Ultimately, always that simple. There's some rules for logarithms. For example, log of A times B is the log of A plus the log of B. You got a multiplication here, you got an addition here. This is very, in some ways, pretty analogous to the idea that x to the A times x to the B is x to the A plus B. You got a multiplication here, you got an addition here. This kind of goes the other way. You got a multiplication here, you've got an addition here. I'm trying to make too much of the analogy, except to understand that there's a reason that multiplication here gives you addition here. The log of a to the b is b times the log of a. Think b is an exponent here that you end up multiplying it by a here. Okay, just like you got exponentiation, sort of becomes a multiplication. And here you got an exponentiation, but here you got a multiplication. Okay. Don't use these to try to remember these, because connecting this to this or connecting this to this is a little above what we try to ask people to do in pre-calculus. Okay. If you're really ambitious, you can work that out. It's not that difficult, but it's more than we need. We've got the rules. The rules are sufficient for what we need. Now, if the log of a times b is the log of a plus the log of b, what do you think the log of a divided by b should be? Well, yeah. I always regarded this as unnecessary because you combine these to figure out what happens for negative exponent and get a negative multiple, and it all goes together to give you this one. Still, those are free rules. Okay. And there's a couple more, like, you know, like the log base 2 of 2 is 1. Okay. Also, the log of 0 is 1. Okay. Any number to the 0 is 1. They write those as rules, but they follow from these rules, so I don't pay that much attention to them, but you probably should. Okay. Let's see how these rules can go together. Solve an equation like log of x plus 1 plus the log of x minus 5 equals 7. Let's make these logs to the base 2, because if it's log logs, the numbers get really huge. Okay. What rule do you see that could apply to log base 2 of x plus 1 plus the log base 2 of x minus 5? You see a place where 2 logs are added up here. Yeah, right there. Okay. So by this rule, this becomes log base 2 of x plus 1 times x minus 5 equals 7. Okay. And of course, we can expand this. Okay. If we convert this using rules here, we can identify b as 2. Well, actually this one, b is 2. C is x squared minus 5x minus 7, because that's what we're taking the log of. And a is 7. Now we're trying to solve this for x. X is trapped inside this log function, but it's not really trapped because we can convert to this form. And if we convert this form to this form, with again, a equals 7, c equals x squared minus 4x minus 5, and base 2, we get x squared minus 4x minus 5 equals 2 to the 7th. Two to the 7th is 128. Can you solve that equation? Yeah, it's a quadratic equation. Now you have to put it in standard form because I doubt this thing's going to factor. Okay, but from here to here, from here, it's just do what you know how to do. Okay, so all we did was we used these rules. These rules are pretty simple. They don't change. You just got to identify the parts and then change from one form to the other. If your x is up here, then you better convert to this form because that gets your x out of the exponent down here where you can operate on it. If your x is inside this C thing, well, you want to untrap it and get it out here. Okay. And then let's say 4 times 130 is 520, 532, and 16 is 548, I think. Okay. X squared 548 is 23.3, something like that. Okay. So you could approximate that. Make sense? So this isn't really particularly difficult. Matter of fact, this is fairly easy equation solving once you get used to using these rules. Now the letters A, B, and C, I mean, B is pretty universal for the base. So whatever rule you see in your text or open math is going to have a B there, I'm sure. It might not be an A and a C, it might be an X and a Y, even. Kind of like X and Y. Because it immediately hits you in a narrower context. More general, but whatever. It's not difficult. Okay. And these rules are not difficult. You just got to practice a little bit, look at a few examples. And this is not something that people usually have much trouble with. Okay. So just keep your wits about you, do the homework, make sure you get the rules down. Okay. So that's a fairly easy assignment, so we still have a test hanging over your head. Okay. Okay, well, we're actually a few seconds early, so we're going to quit here.